The integral from 1 to 2 of the square root of 1 plus 4x dx. Here we are going to apply U-substitution, but it is on a definite integral. We'll start by letting our u be the part underneath the square root 1 plus 4x. So we have u is 1 plus 4x. The derivative, du, is just going to be 4 dx. So we're going to replace this dx with a 1/4 du. We'll divide the 4 to the other side. So we'll have a 4th du is equal to dx. Now here, what I recommend at this point is remembering that you're trying to perform a complete change of variables. These numbers here, 1 and 2 on the definite integral, are in x. So this is technically x equals 1 and x equals 2. And if you think about it like that, when we switch out our 1 plus 4x for u and our 1/4 du for dx, we will not have changed our limits of integration to also be u's if we leave them as 1 and 2. So to perform a complete change of variables, we have to change x equals 1 to a u value and x equals 2 to a u value. So in other words, we're going to substitute in x equals 1 into our equation u equals 1 plus 4x. So we have u of 1 is 1 plus 4 times 1, which is 5. So our new lower limit of integration will be 5. And then we'll plug in 2. So 1 plus 4 times 2, 1 plus 8 is 9. So our new integral will look like the integral from 5 to 9, the square root of u, and then again dx was 1/4 du. So 1/4 du. Now I could have went straight ahead and pulled this 1/4 to the front. So we can have 1/4 the integral from 5 to 9 of u to the 1/2 du. So now we never have to return to x's. We have done a complete change of variables. This is u equals 5 to u equals 9, u to the 1/2 du. So we never have to return to u. We'll just finish this problem off until we arrive at a number. So the antiderivative of u to the 1/2 is u to the 3/2 times 2/3, and this is evaluated from 5 to 9. Let's clean this up here. So 2 will divide evenly into 4 2 times, so I'm left with 1/6 u to the 3/2 evaluated from 5 to 9. So we'll start by substituting in 9, and then we'll subtract substituting in 5. So we have 1/6 and then 9 to the 3/2 minus 1/6 5 to the 3/2. Now we can simplify this 9 to the 3/2 a little bit further. So this is the square root of 9. So we're focusing on the fact that I have 3 divided by 2, so the root is 2. So the square root of 9, that's 3. 3 cubed is 27. So what I would have here is 27 over 6 minus, but here the square root of 5 isn't an integer. So we could really just leave that as that 5 to the 3/2. So 5 to the 3/2 over 6. I mean, we can write this with a common denominator, 27 minus 5 to the 3/2 over 6. And while it's an ugly answer, it is our final value for a numerical answer. Now, this is one choice to convert everything into u's. Some people like to perform our change of variables, but leave x equals 1 and x equals 2, and then return back to x. So if you're going to do that, I would recommend leaving x equals 1, x equals 2 to make it accurate, and then it would be 1/4 the square root of u du. But if you don't put x equals 1 to x equals 2, you're implying that these are x values because of the differential du. So if you want, you can leave these 1 and 2, integrate this, and then plug your u back in, plug in 1 plus 4x, and then plug in 2 and plug in 1. That is a possibility. But I think it's kind of just nicer to just change everything, do a complete change of variables at the beginning, and then you never plug u back in. So right here, once we got to the antiderivative, we just plugged in 9 and plugged in 5, and that was it. Now let's try the integral from 0 to 1/2 of the quantity sine inverse of x cubed all over the square root of 1 minus x squared dx. So this is again going to be a substitution with a definite integral. So the substitution that we're going to do here is we're going to let our u be sine inverse of x. Sine inverse of x. So if u is sine inverse of x, the derivative du is 1 over the square root of 1 minus x squared dx. And we do have that. So another way to maybe rewrite this original problem to help us see it a little bit better is to think about this as 0 to 1/2 of sine inverse of x cubed times 1 over the square root of 1 minus x squared dx. So kind of split it up and think about it as a product. And so now our u, sine inverse of x, is being cubed, and our du is just right there being multiplied. So our du is 1 over the square root of 1 minus x squared dx. So our integrand is going to look like u cubed du, but our limits of integration are currently still x values. So x equals 0 to x equals 1/2. So remember, we can, if we want to, leave them as 0 and 1/2, but we'd have to put x equals 0 to x equals 1/2, because if we just write 0 and 1/2, then we're implying that they are u values, that they match the differential. I'm going to go ahead and change these x values into u values. So I'm going to evaluate what's u of 0. What is sine inverse of 0? Well, it turns out that that's just 0. So you plug in 0 into sine and you get out 0. And u of 1/2, right? What is sine inverse of 1/2? So remember, what we're thinking about is what angle do I plug into sine to get out 1/2? Well, that's going to be the angle pi over 6. So my limits of integration over here are going to be 0 to pi over 6. All right, so now we never have to return to x's. We can just evaluate this definite integral. So the antiderivative of u cubed is u to the 4th over 4. And we're evaluating this from 0 to pi over 6. Well, that's not too bad. We're just plugging in then pi over 6 to the 4th over 4 minus 0 to the 4th over 4. So that's going to give us basically 1/4 and then pi over 6 to the 4th. Here, this is going to give me a pretty big number. So I'd have a pi to the 4th on the top. 6 to the 4th is 1,296 times that extra 4 on the bottom. It's going to give me a big denominator of 5,184.